All right, we're going to do another 2D kinematics problem. I apologize that this one is also about a ball being thrown. That was what I had prepared, and sometimes originality is not how these problems go. We'll have more fun ones on the homework. Okay, so let's say I'll write the problem up and then read it, because that might be, you might be given this problem in words, and it's useful to see how to interpret that. Okay, a ball is thrown from 8 meters above the ground at an angle of 15 degrees above horizontal and a speed of 20 meters per second. So part A asks, how high does it go, implied at its highest point? Part B, how far in the x direction does it travel before hitting the ground? And when we say before hitting the ground, really this means when it hits the ground. At the moment it hits the ground, what is its x position? I'm going to erase parts A and B. We just remember that first we're looking for how high does it go. Okay, so let's draw a picture of this. So we have something that looks like this. We have a ball that's like 8 meters above being thrown at an angle of 15 degrees with a velocity of 20 meters per second. So the ball is going to follow some path like this, and it's going to end at a different height than where it started, and it's going to end at a different x position and different y position than where it started. So when we're asking for how high does it go, we want the height at the highest point. So we want like the maximum y value. So how do we get that? So on our picture, that point is like right here, right? And we want to find what the y value of that point is. And we could get our answer here above where it starts, or we could get it above the ground over there. Either one of those, it doesn't really specify which one it wants, so I would take either one if this was asked this way on an exam or something. Okay, so we want this y value. What do we know about this point right there? Well, if this is its highest point, we know that Vy has to be equal to 0. So that gives us a place to start. So we're probably going to have to do something with the y direction. Let's look at our y variables. Y initial, y final, Vy initial, Vy final, Ay, and T. Okay, so y initial, we're going to say this starts at a height of 8 meters over here. And so we're calling this, we're calling the ground y equals 0. We're calling the top of this 8 meters, so that's starting at 8 meters. Y final, now this is tricky because the final height of the ball, of course, is 0. But for part A, we're not interested in what's going on over here. We're interested in what's going on over here. So we're looking at the motion, we're looking at just the first part of this motion. I don't want to mark this up too bad. So here's the path of our ball, that it's taking off this cliff. We're interested in going from here to here, and we don't care about everything that happens over here. We only care about this for this part of the problem. So y final here is what we are looking for. That is distinct from this y final, which we will maybe find later, which we already know. Anyway, okay. Vy initial, we don't know, but we know enough to find it out, right? We have 20 meters per second speed and an angle of 15 degrees. So this is equal to 20 times the sine of 15 degrees. We'll plug that in just a second. Vy final, we do know because that is equal to 0, right? At this tippy top point, Vy is equal to 0. Ay is equal to minus 9.8, as it often is. And our time, we do not know. So we know enough to solve for what's going on in this problem. So time is the one we don't care about here. We want this, we know all the rest. So you can look at your equation sheet and see that we want to use the time independent equation. Before I erase this, I should write 20 times the sine of 15 is equal to 5.18 meters per second. So it's going up, it initially is going up at a velocity of 5.18 meters per second. Okay, I'm going to erase all this and we're going to plug these into the time independent equation. So that is v final squared minus v initial squared is equal to 2a delta y. Remember, this is what's going on in the y direction. So v final is equal to 0. V initial was 5.18. And that's equal to 2 times minus 9.8 times delta y. And that is what we are looking for, that delta y. So now we can solve this equation for delta y. Delta y is going to be equal to minus 5.18 squared. And remember, the minus sign is outside of the squared, so the minus sign stays there. Divided by 2 times minus 9.8, so these minus signs are going to cancel. Cancel by rubbing it on your finger. And we plug these in and we get delta y equals 1.37 meters. Okay, so what is this delta y that we've found? Well, delta y is y final minus y initial. And here, if I draw our little picture again, this is y initial here. This is y final here, right? So what we have found is the vertical distance between this point and this point. This is what we have just found, delta y. We did call the ground y equals 0. So if we wanted to know what the height of this point was above the ground, we would want to solve for y final, which means we would add y initial to both sides, right? So y final, sorry, I'm going to work up here. Y final, solving this equation for y final, I get y final equals 1.37 plus y initial, which is 8 meters. So that's 9.37 meters. So like I said, either one of these you could argue is a reasonable answer to what it's asking. How high does it go? This is just how high above the ground, and this is how high above where it starts. Okay, so now I'm going to erase everything here because this is getting messy. So part B asks for how far does it go in the x direction before it hits the ground. So for this, my initial, it's not square. For this, my initial position is the same, right? I'm still starting at this 8 meters height, moving at this velocity, but now my final, my final location is this point down here. So what that means is what we just found in the last problem, what's going on at that point, is not really going to help us at all. So we're gonna have to pretty much ignore our results from the last part of the problem, from part A. Okay, so we want to know x final. That's what we're trying to find. How far does it go? Delta x, which if this is x equals 0, this is just x final. So we want x final. And so we're going to have to do something in the x direction. So let's look at what's going on in the x direction. Hopefully some of you noticed my mistake / overkill, whatever here. So these are all of our variables, but because this is a 2D kinematics problem, right away, ax is equal to 0, which means vx final is equal to vx initial, whatever this is. So these two numbers are the same. X initial, like we just said, is 0. X final is what we are looking for. And time, we don't know. Okay, so for constant position, for position, when an object is moving at constant velocity, we only have one equation, and that is x final is equal to x initial plus vt. So we need, if we want x final, we need all of these. We have x initial, we don't have v yet, but we know enough to figure it out, right? It's 20 times the cosine of 15 times, ran out of room, sorry, times t. So if we want x final, we have to find t. There's no way around it. So this is one of those problems where we have to solve something in one direction and plug it into the other direction. So we'll come back to the x direction later. We're going to have to look at the y direction again. So here we are still starting at y initial is 8. Here y final is equal to 0, right? Because now this is our final spot. So let's write down our y variables again. Y initial, y final, vy initial, vy final, ay, and t. So y initial is 8, y final is 0. Vy initial we found in the last problem, that was 5.18 meters per second. Vy final, we do not know. That's how fast it is going down when it gets to this point over here. Ay is minus 9.8, and t, we do not know. That is what we need to get the final answer using the x direction equations. Okay, so again, we're going to want to use the position equation. You can, again, look at your equation sheet and justify that to yourself, but vy final is not important here. We don't care about it. So let's do that. We know all those values. So y final equals y initial plus v y initial t plus 1/2 a t squared. So y final is equal to 0. Y initial is 8. Vy initial is 5.18 times t plus 1/2 times 1/2 times minus 9.8 is minus 4.9 t squared. And now we have a t squared, we have a t, and we have a constant term. This is something that we do need the quadratic equation to solve. I am not going to make you go through the plugging. Well, no, I'm going to make you go through it. I'm not going to make you go through the watching me do it. I'm just going to jump right to the answer. You should, if you're not 100% comfortable, you should practice and make sure you get the same answer I do. So when we solve this equation, we plug it into the quadratic equation box, and out comes two answers. Actually, we have 1.91 or minus 0.85. Those are the two mathematical answers to this quadratic equation. So which one of these do we use? Well, in these problems, we're always starting our clocks at time t equals 0, right? When we're right here, this is time t equals 0. So if we got a negative answer, that means that was at some time before this. So if we follow the ball backwards in time, a negative time is where it would be starting if it kept moving, and when it was at a height of 0 over here. Yeah, anyway, this is not a physical answer is the point. The answer we want is 1.91. And in this case, we can just see it because it's positive. In other problems, there may have to be other ways that you decide which of the two answers is correct. Sometimes maybe it's, if we had two positive ones, one might be when the object is going up and one when the object is going down. Like if we were solving for when the ball was at this height, it's at this height two different times, right? So we would get an earlier solution and a later solution if we were looking at that. Anyway. Okay, so 1.91 seconds is the answer we are looking for, so that is t. And now we can use that with our x direction equation. So remember, in the x direction, we had x final was equal to 20 times the cosine of 15 degrees times t. So this 20 cosine 15 is 19.3 meters per second times our time, 1.91 seconds. And that's going to give us 36.9 meters. So this is its x position when it gets to here. It has traveled a horizontal distance of 36.9 meters. So this has been a pretty good introduction to what's going on in this problem. As a post problem exploration, I wanted to look at one other thing, and that is looking at the velocities. So we said before that our velocity vector is tangent to this like arc at every point, right? So when it's down here, our ball has a velocity that's down and to the right. And we know what one of those components is, right? We know what this x component is because that's staying the same. That's still our 19.3 meters per second. This one, we don't know, but we could plug some numbers in and find out. We know it would be bigger, here it's a bigger downward y velocity than it is here, which is bigger than it is here, which is bigger than it is here, because here it's 0, right? So we could be asked to find the y velocity at this point, where we would take our y velocity equation. So that's like vy final equals vy initial plus a t, and we know everything on this side, so we could plug t and a and vy initial in and find vy final. So we would get some negative big-ish number over there. I don't have the number. I'm not going to do that. The reason I'm asking about this is because it's a very common question to ask about how fast it is going when it hits the ground. So this would be a separate question from everything you've been asked here so far. I just wanted to talk about one other thing I could have asked for. So like, what is the final velocity when it hits the ground? So there we have to worry about, again, the x component and the y component. We can find those individually. A lot of people want to say, oh, well, when the ball hits the ground, doesn't it stop going down because it's not like going through the ground? So at this point, isn't the y velocity 0? And the answer is no, because our kinematics equations only work if we're undergoing constant acceleration, which means they only work if nothing else is touching the object, if nothing else is touching the ball. As soon as the ball touches the ground, these equations aren't good anymore, and we need more sophisticated physics to figure out what's going on. So whenever we're solving these equations, we're always saying, okay, the ball, when the ball gets to the ground, it's just, there's just the tiniest, infinitesimally small gap between them. So it has not yet changed its motion, but it is still, it's still following the same trajectory. It's just when it is at a height of 0, but still hasn't hit the ground yet or whatever, it had a velocity, right before it hit the ground. So that's what we would be asking for if we asked for this final velocity. Okay, very last thing. If we were asked for the final speed, of course, there we would have an x velocity and a y velocity, and we would want to find this component with the Pythagorean theorem. And that's another thing that is asked fairly often in these sorts of problems. All right, so yeah, hopefully this was a good introduction. We'll be doing 2D kinematics in other forms throughout the rest of the course. So this is a very good area to get good at.